In the last section, we looked at the concept of instantaneous rate of change, where we look at the average rate of change over smaller and smaller intervals about a point, and we can estimate the instantaneous rate of change at that point. And we define the derivative of a function to be the instantaneous rate of change at a point. And it's the slope of the graph at that point, or it's the slope of the tangent line to the curve at that point. Now, we can find the instantaneous rate of change or the derivative at any point on a function. And if we put all of those x and f prime of x values together as ordered pairs, we can graph the derivative of a function. Okay, so that's what we're looking at today. We're looking at the derivative as a function. Instead of just looking at the derivative at various points, we're going to put all of those points together and graph the derivative of a function as a function itself. All right, so let's go ahead and look at this first example. All right, we're just asked to find the derivative of the function at various points. All right. Now it's a little bit tricky with all you're given is a graph. So we're just given a graph and we want to find the derivative of these various points. So let's take this first point. It's at x equals -2. So that's about right around there. Okay. Now, best thing I can do is probably just draw a tangent line at that point and kind of estimate the slope of the tangent line. All right. So it's an increasing function. If I want to draw a tangent line, I'm just going to draw something as best I can with my line tool. All right, and then we'll estimate what the slope of this line is. Okay, so, all right, so there's a tangent line. It's probably good enough. So let's just see what's happening here. So if I look at this line, I'm trying to find the slope of this line. If that's a good enough tangent line, then let's see what's happening. I can see that at least the way I drew it, it crosses here, and I go up 1, 2, 3, 4, and maybe about 5. I don't know. It's not quite. It's maybe less than 5, but I'm just gonna say we have a rise of 5 and a run of 1. Okay, so the slope of the tangent line, the line that's tangent at this point where x is equal to 2 looks like it's about 5. So I'm just going to estimate it to be 5. I'm just going to round it up to the nearest whole number. Good enough. All right, that's about as good as you can get. When you just have a graph, you just have to draw a tangent line and just kind of get a ballpark number. All right, so let's do that at each one of these points. All right, -1. -1 is here. Whoops. Let me see here. I'm gonna draw the point first. -1 is here. Now, this one looks pretty easy. I think I could just freehand that one. That looks like it's 0, right? It looks like it's horizontal at that point because that's the point at which the function is changing direction. It's going from increasing to decreasing. All right. Now let's look at 0. All right, let's find the point 0. Okay, right here. It looks like it's 0, 3 is the point. So if I try to draw a tangent line at that point, okay, let's see how well I can do here. Well, it can be a little tricky. I'm just going to draw a line. I'll start with something that looks like it's parallel and then maybe move it over a little bit so it's just touching. Whoops, I guess that's not working very well. Let me see here if I can drag it a little bit. It looks like it's a little too steep, but anyway, just do the best you can. All right. So, all right, now we're going to estimate what the slope of that line is. All right. So let's see what we got here. Kind of looks like it's obviously negative because it's going downhill. And it kind of looks like I'm going over 1 and down. I don't know. I'm going to say roughly 3. So I'm just going to, again, ballpark it, say -3. Okay. It's negative because it's decreasing, right? It's decreasing at that point. F of 3. All right. That's another easy one. That's just right here. It looks like that's the point at which it's turning around. So the tangent line would be horizontal. And then finally at 4, we're right here. And Okay, let's try this again, see what I get here. If I draw a little tangent line at that point. Okay, we'll see how that's good enough, maybe. I can drag this over. I don't know. Guess it's not going to let me drag it. Okay, well, that's probably close enough. So let me go back to the pen tool and see where we're at here. Gosh, let's see. It's supposed to touch here, that midway in between. So 1, 2, 3. It kind of looks like maybe it's 5 again. 1, 2, 3, 4, 5. Up 5. Up 5 and over 1. I'll just say it's going up 5 and over 1 roughly. So I'm just going to estimate it to be 5. All right. So I've estimated the derivative at those x values. All right. Now what I'm going to do is I'm going to create ordered pairs out of these. Right. This is -2, 5. And this is -1, 0. And this is 0, -3. And this is 3, 0. And this is 4, 5. Okay, so my ordered pairs now are x and f prime of x, and I can graph f prime of x now just by plotting these points and then connecting them to form a function. All right, now before I do that, I think there's something here in the middle here which I have to cover, which is if the derivative of a function is greater than 0, right? That means the slope of the tangent line was positive, right? So it's going uphill. Then f is increasing. Okay. If f prime is negative, right? It's less than 0 on an interval, right? That's a negative slope. That's the function has a negative slope. And the slope of the tangent line is negative, so it's decreasing on that interval. If f prime is 0 on the interval, then f is, well, it's neither increasing or decreasing. So maybe I could just say it's flat at that point, right? It's just flat. It has a slope of 0, right? So the tangent line is flat. It's not decreasing or decreasing. So I could say neither increasing nor decreasing at that point. All right, so there are things that we can interpret from the sign of the derivative. All right, now let's go back to what we were doing, which was to take these points and now graph the derivative as a function. All right, so we're going to graph the derivative function. So we have these points. I'm going to copy them down here, right? We have f and f prime of x, and I'm going to graph f prime of x. And the values I got up above were -2, 5, -1, 0, 0, -3, 3, and 0, and then 4, 5. Right? That's what I got before. 4 and 5. All right, so that's my table of values. I'm just going to graph those values. So let's see, -2, 5 is right here. -1, 0, 0, -3. I had 3, 0. 3, 0 is here. And I have 4, 5. Okay. Now you can see I got it's a little asymmetric about that. And that's mainly because, you know, I only took a few points. So let's go ahead and let's connect up what I've got. All right, but you can see I'm kind of missing some values. Now, if you go back up to the function, let's try and figure out what's going on between 0 and 3, right? Because at some point, you notice that the, well, let's see, let's go back up here. So we had, what do we have? Last point was negative, yeah. So we were at 0, 3, and then we skipped over to 3, 0, right? And so we were missing some points. Now you can see it continues to decrease until you get to 3, and then it starts increasing again All right, so the value of the function goes, sorry, the value of the derivative, it's the value of the derivative is going to be, it looks like it's concave up, so the derivative is increasing all the way through here. So we're going to actually come down a little further, and then we're going to go back up. It'll look a little like that. Okay. So that change in that dip here isn't really evident from the points that I selected, but that's essentially what the graph of the derivative would look like. You know, we could choose more points and we could get more accurate. If I knew what the function was, that would be easier, because then I could just evaluate what the derivative is. And that's what we're going to do in some of the future examples. So, but that's the idea. That's the whole idea with this section, is actually seeing the derivative as a function itself.